Welcome, friends. Welcome to my academic program. We were discussing Power System 1. In the last class, we have derived a formula of inductance of a solid conductor, which is we have derived 2 into 10 to the power minus 7 ln d by r dash, where d was distance between two conductors, where distance between two conductors and we have r dash, that was is equal to 0.7788 into r, which is called geometric mean radius, or in short GMR. Now when we consider the return conductor, so this formula will be 4. That means 2 into 10 to the power minus 7 ln d by r dash. However, for practical power system, this formula will not work. Now why? Now what we have discussed, or what we have considered here, we have considered a solid conductor. We consider another solid conductor, which is assumed to be a return conductor. Then we measure this as our radius, and we measure this distance as d. Now in practical case, we don't have any solid conductor like this. We always have stranded conductors like this. I am just representing one conductor like this, and we are representing another conductor like this. Practically, we are using stranded conductor like ACSR. Now let us say we have a central conductor is this. We have a central conductor is this. And let us from the central conductor to the central conductor of this is conductor number 1 and this is conductor number 2. Let us say from central conductor 1 to the central conductor 2, this distance is d. Okay. And let us say let us choose another conductor, let us this. So from this point to this point, let me say this point is x, let me say this point is z, and this point is y. So distance from x to y is d, and distance from x to z is d dash. So d and d dash are not equal. D and d dash are not equal. So when you apply this formula, there would be a problem. 2 into 10 to the power minus 7 ln d by r dash. So which distance should be considered? It is not having only one distance. We have a n number of distance existence in between any two conductors. So there is a problem with that. Again, for same conductor, we have got not only one conductor, we have got plenty of conductors. So everyone has got its r, although they are equal, but in case if they are not equal, then which r should be taken? Which r should be taken? So there should be a problem. So in order to address this, this formula will not work. So what is that? What is the remedy of this situation? As you can see, L inductance is a function of d by r dash. So you see this every possible distance will contribute to the inductance evaluation, every distance. So to have the accurate calculation of inductance, every distance has to be taken care of. So for a power system with stranded conductors, we have a stranded conductor, we have lots of distances are available. Okay, between, it may be between two conductors or it may be between two subconductors. So as it is a function of d and r, each distance will contribute to the L calculation. Hence, this previous formula is modified in this fashion. So previous formula, what was that? L, it is now modified in this way, 2 into 10 to the power minus 7. The first, this constant term is as it is. Now inside the log, now d is replaced by dm and r dash is replaced by ds. D is replaced by dm and ds, r dash is replaced by ds. So what is this dm? What is this dm? It is called geometric mean distance. In short, it is called GMD. And what is ds? ds is called geometric mean radius. Geometric mean radius. In short, it is called GMR. Sometimes this GMD also called mutual distance. Sometimes this GMD is also called mutual distance. And sometimes this GMR is called self distance. Now what are their significance? So we have modified our previous formula by this factor dm by ds. What is dm? dm is geometric mean distance. In short, it is called GMD. Sometimes it is called mutual distance. And ds is called geometric mean radius. In short, it is called GMR, and sometimes it is called self distance. So this formula, as I already told you, this formula has been replaced by this term dm by ds. Now what is dm? What is dm is actually doing? It is very important. It essentially computes the mutual distance between any two phases. What do I mean by that? It computes mutual distance between any two phases, whether it may be A to B, or it may be B to C, or it may be A to C. Any distance between these two phases can be defined as the mutual distance. What is ds? What is it doing? What is the role of this ds? It essentially computes the self distance of any phase. What do you mean by that? It either computes the distance of A or B or C. You know, as this term comes mutual, so you know mutual is meant by between any two objects. So that is why it computes in this distance between two phases, either between A to B or between B to C or between A to C. And Since self is defined, or self is meant by only one object or one person, so it is the distance of only one phases, A, either A or B or C. Now this GMD GMR method is quite useful, very useful, to calculate L and C for any geometrical configuration. Now we may have different geometrical configuration in our power system. We may have single circuit line, we may have double circuit line, we may have double circuit line. Now out of these two, we may have symmetrical spacing of between conductors, we may have symmetrical spacing between conductors, we may have unsymmetrical spacing between conductors, or any other configuration. This GMD GMR method will work absolutely fine for every possible geometrical configuration. This is number one advantage. And second advantage is that, this is number one advantage we have with our this GMD GMR method. And second advantage is that it is free from any complex mathematical derivation. You should not do any derivation. You should not do any complex mathematical derivation for this type of power system topologies. Okay, so this mainly attracts the main advantage of this scheme. It is work absolutely free, irrespective of the tower configuration, whether we have single circuit line or we have double circuit line, whether we use bundle conductor, whether we use stranded conductor, whether the spacing between the conductors are symmetrical, whether the spacing between the conductors are unsymmetrical. Everywhere it will work absolutely fine. And most importantly, you should not calculate any, or you should not derive any complex mathematical derivation for any of these tower configurations. Okay. I will show later, I will show by problems that this, how this GMD GMR method is effectively used suitably to calculate inductance or capacitance of a transmission line. But one thing, provided that you should follow certain rules. You should follow certain rules. So once you will follow those rules, this method is extremely useful. This method is extremely useful to calculate inductance and capacitance of any transmission line. Now coming to what are the rules? What are the rules? Now suppose, let me tell you one thing, that you see, this is, let us say this is a three-phase double circuit line. Okay, let us say this is a three-phase double circuit line with symmetrical spacing. This is three-phase double circuit line with symmetrical spacing. Let us say this is conductor A1, let us say this is conductor B1, and let us say this is conductor C1. So these are A, B, three phases of circuit 1, and this is C2, B2 and A2. This is A, B, C phases of circuit 2, and these circuit 1 and circuit 2 are running parallelly. Now you see, it's suppose this distance, maybe it's between A1 to B2. This distance is called mutual distance because it involves two phases, two different phases. Whether let us say this distance, okay, let us say this distance maybe from you know this C1 to C2. This distance defines to be self distance because it involves same phase, that is the C phase. Now you see, although they are the different conductors, but they occupies the same phase because this A1 A2, they are occupying same phase, that is phase A, that is B1 B2. They are occupying the same phase, that is B, and C1 C2, they are occupying the same phase C. They are different conductors, no doubt, but they are emanating from the generator terminal, A terminal of the generator at the generating station. So they are emanating point are same. That is why they belong to the same phase. Same for B and same for C. So any distance between C1 and C2, B1 and B2, and A1 and A2. So any distance between A1, A2, B1, B2, and C1, C2, they are defined to be ds. And any distance to be measured between A1, B1 or A1, B2, something like that. So it involves two phases. They will be treated as dm, that is mutual distance. So what are the rules? Now first rule is that you should identify the possible distances. You should identify the possible distances exists between two phases or same phases. Okay. Now, what is mutual distance? It defines any distance between two conductors of different phases. As I already told you, it is between either A to B or B to C or A to C. What is self distance? Self distance ds defines any distance between two conductors of same phases, whether it is A1 to A1 or A1 to A2. In a moment, I'll tell you what is A1 to A1. A1 and A1 to A2, it is well understood, this distance. A1 to A2, it is well understood, this is this distance. But what is A1 to A1, I'll tell you in a moment. Now, once you have identified all the possible distances, you should calculate the geometric mean. What is geometric mean? Suppose you have n number of distances with you. You have D1, you have D2, you have D3, up to you have Dn. So you need to take product of everything. You need to everything, that is the n number of terms. Then you should take nth root. You should take nth root of that product. So this is the general, this is the general term, or this is the general formula. So if you have the, if you have n equal to 2, if you have two terms, then you should take d1, d2 under square root. So if you have three numbers, then you should multiply d1, d2, d3 cube root. If you have n equal to 4, then you should take fourth root of d1, d2, d3, d4. So it is the practice. So you should calculate the geometric mean. What is geometric mean? You have to identify the number of terms existed, then you take the product, then you take the nth root, that is the number of term. Okay, n is being the number of term. And always remember this, when you calculate the third rule being, when you calculate the inductance, always consider S is equal to 0.7788 R. You should not consider R for inductance calculation. Okay, these three are the rules we should follow to calculate any inductance and capacitance of any tower configurations. So with this I am ending this lecture. In the next lecture, I will show you how this GMD GMR method can be utilized to solve a practical problem. Thank you. Looking forward for your next class.